Yes, good evening to everyone. Today we'll be discussing about reaction turbine. And reaction turbine has a series of fixed and moving blades where we see the pressure is being distributed. That means the change of pressure and in comparison to that of the in relation with the pressure and the velocity. The velocity will be continuously changing. It will not be changed all of a sudden. Okay, the variation will be taken place in stages. That is a need why we go with the alternate arrangement of this moving and the fixed plate and the reaction turbine. Now we will look at some few of the points where we are concentrating more on the reaction turbine when compared to that of a impulse turbine. Okay, now we'll start the session. Coming to this, in reaction turbine, the steam expands continuously. Here, what happens? Steam will be steam is expanded continuously. Where it is being expanded continuously over fixed blade and moving blades. Right? When compared to that of the impulse turbine, they we don't have the continuous expansion of the steam, right? Now this is said to be the reaction turbine, where there is a continuous expansion of the steam over a fixed plate and a moving plate, right? Therefore, under this condition, we have some relations. We have to remember this relation. The relations are VR2 is always greater than VR1, right? And in this Parsons reaction turbine, the fixed and the moving blades are made identical. Here, this is the first note, and the second note is like both the fixed. We have two types of blades here, right? Fixed blade and moving blade. These two are identical. These two are identical, right? And now, with this condition, still further moving. Third is like alpha equals to pi. Now we will see what is alpha. Alpha is the outlet angle of a fixed plate. Now what is pi? Here pi represents outlet angle of a moving blade. Right? And fourth relation, theta equals to beta. We will see what is theta. Theta equals to inlet angle of a moving blade. Now beta. Beta represents inlet angle of a fixed blade. Fixed plate. These are the conditions that we have to remember. Just see once again, in the reaction turbine, there is a continuous expansion of the steam over fixed plate and the moving plate, right? With this continuous expansion of the steam over the fixed and the moving plate, we have the condition VR2 is greater than VR1. That means that the relative velocity at the outlet will be greater than that of the relative velocity at the inlet, right? And the second condition is like the fixed blade and the moving blade, both of them are identical in shape. And the next relation that we have is like there's a relation between the nozzle angle and the blade angle, right? That we converted as a moving blade and the fixed blade, right? And now this alpha represents the outlet angle of a fixed blade, and the pi represents outlet angle of a moving blade. Am I clear? Now here I am going to consider alpha equals to beta, where alpha is the outlet of a fixed blade and pi is the outlet angle of a moving blade. How can you say that? Just look at the blade. If this is one of the blade and this is the second blade fixed and this is the third blade. Now the outlet here, the outlet angle of a moving blade, this is the moving blade and this is the fixed blade, right? Again this is moving blade. What is the condition we have here? Alpha equals to beta. The outlet of a fixed blade is equal to the outlet of a moving blade, right? Outlet angle of a fixed blade is equal to that of the outlet angle of a fixed blade. That means here what is the angle you are going to have here? It is nothing but alpha, or you can represent it as pi. Outlet angle of a moving blade is equal to that of the outlet angle of a fixed blade. Am I clear? Where is the outlet point here? This is the fixed blade, this is the outlet of a fixed blade, and this is the outlet of a moving blade. These two angles are equal. Similarly, theta equals to beta. What is theta here? Here this is the theta. It is the inlet angle. This is theta, and here theta, it is theta, and this is the inlet angle of a moving blade. And where you want to represent this beta, it represents the inlet angle of a fixed blade. Where is the inlet angle here? Inlet angle of a fixed blade. Here is the inlet angle, and this is represented as beta. Am I clear? Here the pi and alpha are the outlet angles of a moving blade and the outlet angle of a fixed blade. Coming to theta and beta, these two are equal. The inlet angle of a moving blade is equal to that of the inlet angle of a fixed blade. These are the conditions that we have to follow while resolving the problem statements under reaction turbine. Okay, and now according to the velocity diagram that we have, and the condition is like the blades are symmetrical about a vertical central line, the velocity diagram for any of a reaction turbine is drawn in similar way how we have drawn to that of impulse turbine. Am I clear? Since the two blades, what are the two blades here? Fixed blade and moving blade are symmetrical. Symmetrical, right? These two are symmetrical. Then what we are going to say that the velocity diagram of the reaction turbine is drawn similar to that of impulse turbine. This is the condition. When we can have this condition when both the fixed plates and moving plates are in symmetrical to each other, right? And now according to this, we'll derive the relations for certain expressions. What are the expressions we are going to see? We are going to derive, we'll see one after the other. First one, work done. Work done per second. Work done per second is given as m multiplied by VW1 plus VW2 multiplied by U divided by 1000 kilojoules per second. Is it the same relation that you have for the impulse turbine? Yes, you have the same relation or the expression. Work done per second equals to m multiplied by VW1 plus VW2 whole multiplied by U divided by 1000. What is m here? M is the mass flow rate of the steam. And what is this VW1? VW1 is the velocity at the inlet. And VW2 is the velocity at the outlet. And here what does this U stands for? It is the velocity of a moving plate, right? And 1000 means it is expressed in terms of kilojoules, so that we have divided with 1000, right? And this is the expression that you have for the work done. Okay, now we will see the second relation. Second relation is for power developed. Is for the power developed. Power developed relation is the same that of work done per second m multiplied by VW1 plus VW2 whole multiplied by U divided by 1000 in terms of kilowatts. These are the two expressions that we have for the reaction turbine. What are these two reactions? One is the work done per second m multiplied by VW1 plus VW2 whole multiplied by U divided by 1000 kilojoules per second. And the second one is power developed, and the power developed, the relation is given as m multiplied by VW1 plus VW2 whole multiplied by U divided by 1000 kilowatts. These are the two expressions coming to find out the efficiency of your reaction turbine. Efficiency will be again in terms of work done per second or the power developed. Okay, is this clear to everyone, ma'am? Thank you. I'll continue the class in the next part. Thank you.